we need a quantum theory of gravity, which is what I've done all my life. I've been paid all my life coming out with the quantum theory of gravity. You approach the horizon of black hole, and the first thing you notice is that time goes funny. And the more you go close to the black hole, the more you see what's going to happen on Earth speeding up. So while on Earth there is 1 hour passing, for you it's only 1 minute. You see rapidly the future of humankind. If people on Earth were looking at you, they would see you moving very slow.
Hello and welcome to Unfiltered. My name is Ollie Dugmore. My guest today is as close to a rock star of theoretical physics as it's possible to be, who's credited LSD with sparking his interest in the subject. He's also a philosopher of science, whose book, 7 Brief Lessons on Physics, was translated into 41 languages, selling over 1 million copies worldwide. His work on the quantum loop theory of gravity has seen him pick up where Einstein left off, and features in his new book, White Holes. With prose so lyrical that he could have been a poet if not a physicist, his latest release journeys to where time and space end, the heart of a black hole. My guest today is Carlo Rovelli. Carlo, how are you?
Thank you very much, Ollie, for this super nice introduction.
Was it okay? Yeah?
Oh, too good.
Yeah? Well, I'm glad to hear it. Sometimes when you, I don't know, I've said this before, but you do an intro and then you pick up on the body language of the person listening, and sometimes you think, oh my God, have I said something that's offended them or whatever. But I think there it was okay. I think it was all right.
Only a bit embarrassed.
Okay, good. Maybe some more embarrassment to come. How are you? What have you been up to in recent days and weeks?
Wonderful. I'm here in London, but came a few days ago from another London, Canada, Ontario. It's near Toronto, so I'm slightly jet lagged, a little bit groggy, but everything's perfect.
Fortunately, we have some very light subject matter to talk about today, so I'm sure the jet lag won't be a problem. Before we get into kind of the subject matter of the book, and it is substantial and theoretical and incredibly important, there is also this question that I'd like to delve into first, though, about the sort of the role of physics currently in mainstream culture, because we've had this big film out, right, over the last couple weeks and months, Oppenheimer, and sort of, theoretical physics making its big screen debut. Have you seen the film, I wonder?
Yes, I've seen the film. Actually, I've seen it, the screening, the premiere, the first presentation in New York, together with Christopher Nolan, and I was in a panel with him commenting just after. Mm-hmm. So I had the full experience. And
what did you think of the film? I'd be surprised if you came and said now that you didn't like it very much if you sat on the panel with him. But what did you think of it? Well,
of course, with him next to me and all the journalists said it's fantastic, it's wonderful, it's marvelous. It is good. I did enjoy. I think it's interesting. Because it talks about science and physics and the effect on society and the interplay between our knowledge that grows and the rest of our life, but also because it raises crucial issues, right? That was the film is about the making of the atomic bomb, so about the entering the nuclear age in which we are, right? So and the nuclear bombs are all over the planet right now, pointing to one another. And determining what's happening and creating a huge, immense risks for all of that. Mm. And Oppenheimer, the main character, who is a man who sort of organized the full large-scale industry for making the first bomb, in his life, and in the movie, of course, he called for global international cooperation. He saw the creation of the atomic bomb even as an opportunity for humankind to stop this idiotic thing of making war to one another and to get together and just find agreements. Politics, fight, but fight in words, not massacring one another. And his point was nuclear weapons are so horrible that maybe humans now could realize that collaborating is better than fighting. Hasn't happened, and we're still there.
There were a couple of things from the film that really stood out to me. One was that exploration of guilt. When the physics moves off the chalkboard and into the real world, and whether or not, but how culpable, how responsible he is for discovering / creating something. But just because he's the person that was involved in the project doesn't mean that someone else wouldn't have found it, or that the laws of physics remain the same, right? If you're the first person to find out about something, does that make you responsible for it? I enjoyed its exploration of whether or not he was guilty, and how he felt about it. I don't know if you felt similarly or something stood out to you.
Definitely. I think it's beautiful, this moral confrontation that he and many other physicists of his generation had with what happened. I mean, they were involved in the middle of the war and Nazism and this and that, and the complications, the eternal complications of human relations. But they seriously, at some point, said, "My God, what we have done, we have contributed to the destruction of tens of thousands, of hundreds of thousands people alive, and creating this thing that could destroy humankind." I wish that this same sense of morality was in all areas of society, okay? Because as correctly in one of the dialogues of the film, Oppenheimer talked with the President of the United States. And the President says something like, the people in Japan who got the bomb on their head don't really care about who built the bomb, who sent the bomb, who decided to drop it. So the responsibility is common. And I think that's where the responsibility should be in politics and in each one of us. We're all involved, I think, because we choose a politician, because we participate to a global conversation about what to do with that. The topic of responsibility is fundamental, not just for the scientists, also for the scientists, but for everybody.
I think that's so relevant, particularly to a British audience, because, again, not talking specifically about the film, I enjoyed the contrast in the film between the sort of the narcissism of the politicians and the kind of the expertise and perhaps humbleness, maybe that's not the right word, humility of the scientists. And in British politics in the last 10, 15 years, there's sort of been this, call it a war, a sort of a war on expertise. One of our most high-profile politicians, Michael Gove, during the Brexit campaign, he said the British people have had enough of experts. And at the time, people were very confronted by that statement. They said, what on earth do you mean we've had enough of experts, we've had enough of science? No, these things are fundamentally important to who we are as a society, about our politics, what we value, truth and reason. And it's very easy to say that, but your point there, that actually the responsibility is common.
Yes.
If the politician verbalizes a statement like that, the electorate still decide, whether to vote for the political project that he's advocating for, or to put him in office. And actually to simply say, you said it, you're responsible for it, kind of denies any culpability or guilt for the broader population, right? It distances yourself from something that perhaps you actually are quite directly involved in yourself.
Absolutely. I mean, this country went, for instance, through a drama of the Iraq War, right, in which I believe, I don't live in this country, but I believe a large part of the population now think it was a mistake. And
Absolutely.
It was motivated by a lie, which is the weapons of mass destruction. And politicians were blamed for that. But who chose those politicians?
It's a very difficult question, isn't it? Obviously, it's the electorate, it's the people.
Right.
You point the finger and say, "Oh, it's the politicians who made the decision." But
right, politicians, of course. Well, we need politicians. I'm not arguing against politicians. We need politicians, but we need to choose them widely. Politicians have the job of listening, of course, listening to science, listening to expertise. If they don't, they just do damage to all of us. But then they're one who decide, and they decide by trying to mediate between different push and interest and values. Very often they are not the values of the people, the values of an elite, a minority, of power, of money. But they are there trying to make the decisions, and very often they make the wrong decisions. And in the movie, in the same dialogue with the president, there's another very interesting detail, which is that Oppenheimer says we are in the 48, 49, I don't know when, I don't know exactly. Oppenheimer said, well, soon the Russians are going to have the nuclear weapons as well. So he's making the point, let's deal with that, okay? Let's do something about that. The president starts laughing and say, no, come on, and Russians are never going to get the nuclear weapons, ever. Which make the point that politicians are wrong, okay, very often. So I think choosing politicians wisely and not always thinking that they know better than us.
Mm.
It's important.
Do you think his being an outsider, his being a sort of an alternative thinker, do you think that played a role in him making a great leap of science? Do you think being an outsider is something that leads to, significant development of theoretical physics, chemistry, any field? Do you think being an outsider, breaking away from orthodoxy, there's an important role to be played there for something like that?
Some of the great scientists were to some extent on another outsiders. Some were not. Were very much in the system. Always when there's a jump ahead, there's always an element of breaking the established view, so to say, because that's actually the part of science that fascinates me the more, right? So I'm not interested in science because it's a body of knowledge, a set of books where you can open and read how things go. I'm interested in science because it's a process where you constantly challenge what is written in the book. That's what I find it interesting. So, respectively of the actual individual history of a person or of a scientist, all scientific steps ahead have been breaking with an established view and showing that something that was considered right is actually wrong. When I teach, I always tell my students, right? I mean, you have to learn what I'm teaching you because that's how you build something. But be aware that for sure in what I'm saying, there's something wrong. I don't know where it is. It's up to you find out, right? Because otherwise you'll never go ahead.
And how do you see yourself fitting into that, not just as a teacher, but as someone who is also challenging orthodoxy and, writing about theoretical physics? How do you...
There is a small side of me that has always been an outsider because I was rebellious in my youth, and I came into science after a period in which I was more interested in changing the world. This was the 70s, the moment in which the youth wanted to change the world and thought it was it could do it. It was a disappointment, and I guess I got into science a little bit because of this disappointment, because in science revolutions happen and actually succeed. And it was the revolutionary aspect of science that fascinated me. When I got to study the physics of the 20th century, Einstein and quantum mechanics, the same physics that Oppenheimer is fascinated about, I thought, wow, that's absolutely fantastic. Because it challenges our worldview. It challenges whatever was talked before. It shows that things are different. And I loved that. And I wanted to understand that, to understand what was understood about the world with this new perspectives. And then at some point, along this fascination, I realized that there are a lot of open issues at the core of our understanding of the world, of the physical world. And I thought, I want to be part of this process, this changing our understanding of reality. And that's how I got into science.
We will obviously talk more about quantum physics in a moment, but just in your answer there, you said that in the 70s, you and your generation wanted to change the world, but also believed that you could change the world. Am I right to infer from that you don't think that's the case now, that a younger generation doesn't want to change the world, or they don't think that they can? What's the difference? Or am I picking up on something that perhaps wasn't there in your statement?
No, you're right, exactly. I feel that the young generation now is less optimistic about the capability of making a better world.
Why do you think that is?
I think they're wrong. I think they can very well make a better world. They just have to do it. I mean, I consider myself an old guy at this moment, but I trust the young people. I mean, I see the majority. I live with students, right, at university. They are, on average, far more knowledgeable than my generation. They have a wider worldview. They are more smart because not just in terms of pure intelligence, but in terms of you know more about the world. You have read more stuff. You have more easy access to all sort of information, also very high quality information. And then, of course, you have a deeper perspective, deeper understanding of the world than what we had as young kids. So I like the new generation. From my perspective, an old guy, I wish they were more courageous and not just being worried about their own individual future, but think about collectively that we can make a better world. The world in which we live, which has a lot of shit and a lot of good, all the good is there because people changed what was before and fought for it. And I think this is going to happen and continue. But I don't see it going on very much. And there is. I mean, there are people who fight, the young people who fight and who see the problems, right? For instance, I don't know, there's all a part of youth that is enormously concerned correctly about climate change. And they are screaming about that. So these are, kids that have their eyes open and say, look, there's a problem. You adults, idiots, what are you doing? Fighting against each other instead of just taking care of the real problems.
It's interesting. I agree with your analysis. I wonder how much of a role we're talking already about the 70s and the 60s, right? The counterculture and the individualism of the 60s and 70s, how much that feeds into the sort of individual politics of the now, and whether or not that individualism carries through sort of particularly products like the iPhone, all of Apple's products, Steve Jobs, he was really motivated by that individualism, that counterculture. And now whether or not that's sort of a barrier to the collective action that we're kind of bemoaning, the lack of collective action that we're kind of bemoaning now. It's interesting that the two sort of potentially revolutionary moments and sort of completely how their ideology connects to each other, I find quite interesting.
I don't know.
Well, let's talk about your book then.
Revolution is an old mole that disappears underground, but then reappears when you don't expect it.
And surfaces again. Okay, let's talk about physics.
Yep.
Rather than politics. For someone who doesn't perhaps understand or know what quantum physics is, top line, can you explain to, I don't know, first day in your classroom, what is quantum physics?
No, I can't. Because you started by saying, for someone who doesn't understand quantum physics, and if you really want to understand it seriously, all the way through, then I'm sorry, nobody understands it.
Yes.
Richard Feynman, which is probably the greatest scientist of the second half of the last century, put it very strongly. He says, nobody understands quantum physics. What does this mean? It has to be taken in the right sense. We do understand quantum physics very well, in the sense that we can work with it very well. I mean, we have a set of basic equations and tools and concepts thanks to which we can describe the quantum phenomena. Quantum physics means that matter, everything, displays some peculiar phenomena that were not known before, especially when things are small. And these phenomena, which are quantum phenomena, are well described by the equations, can be predicted. We know when they happen, how they happen, and we build machines with that. We need iPhone is full of quantum stuff inside, all sorts of things, and plenty of our technology has little quantum stuff inside. Transistors are designed using quantum mechanics. So it's not that we don't understand quantum mechanics in this sense. But what happens with quantum mechanics is funny, because these systems that we describe, like a transistor or a laser, or we treat them like black boxes. We know that if we do that, this will happen later on. If we ask what I'm inside, it doesn't make any sense. And there are a lot of explicit situations in which this is like a punch in your nose. Okay. For instance, the most famous one is the so-called double slit experiment. You have a particle, you throw it the other side of a wall, and there are two holes in this wall. And every time you detect the particle is one place. Okay. And if you look where the holes are, you either see it going through one place, one hole, or through the other hole. Okay. But if you want to calculate where you're going to find the particle the other side, you have to assume that it goes through both. Okay. And now you look at me with open eyes and say, what the hell are you talking about? Exactly. What the hell am I talking about? And physicists are confused themselves. So when they compute where the particle is going to arrive on the screen the other side of the wall, they can predict it with absolute confidence. What exactly you send this particle, you say so many are going to arrive here, so many are going to arrive there. Okay, and in the calculation, you just imagine that the particle splits and goes through both walls and then come back the other side. And then you say, but why do this calculation if the particle you always see in one place? And the answer of physicists is because it works.
Don't ask the why. We get to the right place in the end. It's all right.
Exactly.
So how much then is it right to understand theoretical physics as kind of the explanation of what we know, but it's always up for debate, it's always up for challenge, and also can constantly be sort of evolving and moving forward?
Quantum mechanics is a peculiar thing because it's not a typical thing. The typical thing that has happened historically, including relativity, including black holes, including electromagnetism, including Copernicus, including the big jumps, the atomic molecular theory of gases, is that physicists come out with a outlandish new way of thinking. And at the beginning, everybody's confused because it doesn't make sense. But then it slowly it does make sense. You just have to arrange your mind, your neurons. So, let me give a relatively simple example, which is the Copernican revolution. Right. So you start off by saying we're sitting on a chair in the Earth. The Earth does not move. Right. It's not moving. Our chair is not moving.
Absolutely.
Okay.
Yep.
And then Copernicus comes out and, fishes an old theory of antiquity and makes it and shows that no, it makes much more sense that we're actually spinning. The Earth is actually spinning on itself super fast and is orbiting around the sun super fast. So Copernicus comes in and says, you and I are moving at 10 kilometers per hour. And you say, well, what the hell? We're not moving at 10 kilometers per hour. We're not moving. Okay. So total confusion. But now we're not confused anymore. We understand that it's okay. It makes perfectly sense that the Earth is spinning, it's going around the sun, and yet you and I have this sense of not moving. We found a way to bring all together in a conceptual manner that makes sense. Or even before. Right? Let me step one step even before. Long ago, much earlier than that, somebody came out with the idea that the Earth is round. Okay, and there are people in Sydney which are upside down. And how come the hell people in Sydney live with their foot up and their head down? I mean, that doesn't make sense. They would fall, first of all. How can they hang to the feet, to the floor, to the ceiling in that silly way, right? So total confusion. But then, no, we understand. There is attraction, so if you're in Sydney, it looks the other way around. It looks that we're upside down, and so on and so forth. So each one of these steps is a rearranging of reality in a new way that it seemed to clash our common sense, but actually it doesn't. It's our common sense which is a bit restricted. Once you enlarge it, it makes sense. And so through these, century after century, fundamental science have developed a deeper, better understanding of the world. And part of this has just being absorbed in our common sense. In fact, our common sense, it's the absorbed part of our knowledge. It's the part of our common knowledge which is everybody has clearly in his or her own mind. Then there are things which are well understood by the scientists, like black holes or general relativity, Einstein revolution, and the public still struggle a little bit, but they're clear. Quantum mechanics is a bit different because the scientists themselves haven't been yet able to come out. Maybe it's just a confusion, right? Like Sydney people being upside down. It's that sort of confusion. I'm optimistic that with more debates in quantum mechanics, we're going to, in a decade or so or two, say, okay, now we got it.
We figured it out.
Yeah, we figured it out.
Close the book, job done.
Yeah.
Okay, let's talk then about sort of that breaking the confusion, expanding the limits of sort of human understanding. White holes.
White holes is so let me continue this story I was giving you. In this process of learning more about the world, there is a part which the scientific community has found it convincing. Today, it includes the the result of Einstein investigations, which is relativity theory and general relativity theory of space-time, which includes black holes, expansion of the universe, gravitational waves, all that stuff, and includes particle physics, the discovery of what is the little bricks, in a sense, that form matter, the protons, electrons, the quarks, that's out, and quantum mechanics. That's what we know. But then the process continues. We're not done yet, of course. And in fact, I believe that we're not done by far. There are plenty of things we don't know about the world. And out there are clearly things which escape this sort of basic set of theories that we have. And one of the things that clearly escape is the interior of the black hole. And that's where the idea of white hole comes in. So it's not a established theory. It's an hypothesis of something that may happen beyond the current theories. And the white hole, it's a research. It's an ongoing research. Is a speculation. Is a tentative theory, right? Waiting to be confirmed. And what is about the theory of black hole is a white hole is about what happens deep inside a black hole, which is where we don't know what happened.
Mm-hmm. And there's a problem here, isn't there? That sort of even as recent as sort of 20 years ago, many physicists didn't even believe that black holes existed. Right? They didn't think that they were real. One wasn't photographed until 2019. And like you were talking about there, in the book, you take us inside one and eventually out into a white hole. This is a slightly broader philosophical question, but how can we know that something is real, or how can we picture it if we haven't seen it? If you follow what I'm saying, how do we say to those people 20 years ago who go, these aren't real, it doesn't exist, without the photograph? How do we convince them that it is?
That's a fantastic thing about theoretical physics, that it works so well. It has always worked so well. Take Maxwell. Maxwell, he took all the results that Faraday in his laboratory were collecting, but just measuring how little pieces of iron and copper and things moving one with respect to the other were pulling and pushing one another. So he was studying electric forces and magnetic forces. And Faraday has this vision of how they could interact through some sort of diffuse thing that he called the field, the electric field, magnetic field. And Maxwell put all this together and wrote this equation and thought, well, for this to work, the equations must be such, and there should be other terms, blah, blah, blah. And then look at the equation, says, and therefore a consequence is that there could be radio waves. Okay, so people could have asked him, what is radio waves? Because nobody had mentioned radio wave. Nobody knew what radio wave is. Something that come out from the equation. Okay, it was not something humankind had observed before in any manner. The only thing wavy that humankind knew was light, but radio wave is something else. So Maxwell predicted that there are radio waves. Namely, I'm here and I can move some electric stuff, and you're very far away, you're in New York, and you get the message. Okay, we can talk by radio. And boy, it was true. Hertz discovered that, and Marconi did the first transmission from Europe to New York with radio waves. These radio waves were not discovered; they were predicted by theory. And this is pretty spectacular, but things like that happen all the time in science. And what is it going on? Well, what's going on is that we're smart, right? We're doing the same thing that, when we were, hunters in the savannah 500,000 years ago, or whatever, we were looking at some traces and say, look, oh, there is some steps here, and then there is something broken there. Therefore, there should be something which I haven't seen. There should be a little antelope that is going there, right? And you go and you find it. Okay, it is there. How do you get it? Well, because we're smart. From the sign, to make the story coherent, there should be an antelope. You go, you kill it, and you eat it. So it's the same thing that we do in our life, to use partial information and combine it in a way that makes sense and be able to predict something else. And that has worked over and over again. Einstein was sitting in his office all the time and taking the information about what Maxwell had discovered, which I just described, and what Newton had discovered a couple of centuries before, and thinking how the thing could stay together. They didn't seem to stay together well. And he realized that to stay together well, one possibility was this thing that we call his theory now, general relativity, namely that space is curved, time is curved, clock go at different speed depending on where you are. So he wrote down on a few papers in 1915, saying, oh, that's the theory that makes everything together. And the theory predicts that if you take two clocks, you move one up and one down, they go at different speed. Nobody had observed this before. Now we can do it. We have good clocks, and they do. They go at different speed. The theory predicted that there are gravitational waves, and gravitational waves were found. Predicts that the universe is expanding, and bingo, we saw the expansion of the universe. Predicted black holes, and black holes were there. And some of these predictions were so outlandish that they were not believed. Some of the consequences of his theory, Einstein himself did not take them seriously. For instance, black hole, the theory predicts black hole, the possibility of black holes. But Einstein could not understand well his own theory, because to actually open up the equations, to do a calculation and get the right way of thinking about that takes time, takes many people. So Einstein never took the idea of black holes seriously. He died in the 50s, and at the time, black holes were just basically a funny solution of his equation that probably doesn't mean, almost certainly doesn't mean anything. But then in the 70s, looking at some stars, some astronomers, looking at some stars that were moving funny in the sky, said, what's going on there is not comprehensible. You know, there were some little stars that were sort of dancing around something else. So how can a star just dance around something else? A star cannot move back and forth just by itself. There should be, it could orbitate around something else. But what is this something else? It was not visible, so it should be dark. Very dark and massive, because the star should orbit around it. So what could be small and dark and massive, okay? And somebody said, could it be a black hole? This funny thing predicted by the theory? And somebody was saying, oh, come on, that's too strange. And this went on and on and on. And now with getting better of technology, telescopes or radio telescopes, now everybody's convinced that yes, there are black holes, exactly the thing predicted by the theory. And this takes us back to white hole. Because white holes are today in the same situation in which black holes were 30 years ago or 40 years ago. Namely, they are predicted by Einstein theory. They are also one solution of the Einstein equations. And all through my life, I've heard and read in book, yeah, but this is it's a strange solution. It's unlikely that there is anything like that in the world. And maybe that's wrong.
It feels like it's waiting to be disproven then. So I would ask you if you could take us sort of on a journey through a black hole towards a white one, and if you could start perhaps by telling us sort of what happens as you approach the horizon, right, of a black hole. What do we experience as we sort of come up to this point before we start moving forward?
Yes, so let me start by telling you what we know well, what we're confident. So no speculation here, it's just what we know. You approach the horizon of black hole, you go in a starship, you get close to the horizon of black hole, which is possible, just an issue of money, right? Just building a starship and traveling there. And the first thing you notice is that time goes funny. Namely, if you keep communicating back with Earth, you see what's going on in Earth to sort of speed up. Like everybody was moving more faster, like from Earth they send message to you once a day and you receive it once an hour. So you see the future, like you feel like you're seeing the Earth in the future. And the more you go close to the black hole, the more you see what's going to happen on Earth speeding up. And why so? Because where you are, near the entrance of the black hole, time goes slower than on Earth. So while on Earth there is 1 hour passing, for you it's only 1 minute. In your feeling, your clocks, in your oscillation, your heart, your thought is only 1 minute. So in 1 minute you see one other of the. The more you get closer, the more this is strong. So if you go very, very close to the black hole, you hover there with some rockets, you see rapidly the future of humankind. You know, everybody loving each other, peace finally, and the happy future of humankind, or else, whatever. You can enter because for you time goes normal, right? It's not that for you time slows. The slowing of time is only relative to the Earth. If people on Earth were looking at you, they would see you moving very slow. Okay?
Yeah.
But you feel normal, and you go through the horizon. You're inside, and inside, you see the interior of the black hole, which is well described by Einstein's equation, so we know what it is, which looks like a very long tunnel, an extremely long tunnel, a pit that goes down and down, and finite, but very long, which is closing over you very rapidly, and you get squeezed inside until that's where we don't know. And better, that's where Einstein theory is not sufficient. And here is when we have to make the jump and get to something new. And here is quantum mechanics comes in, because there, deep in when you're squeezed inside this shrinking space around you inside the black hole, it's where quantum effect becomes important, and where we need a quantum theory of gravity, which is what I've done all my life. I've been paid all my life for coming out with the quantum theory of gravity. So the tentative theory of gravity we have, loop quantum gravity, on which I've worked all my life, tentatively tells us what happened next. And what happened next, we're inside, right? We're being squeezed. What happened next is that, thanks God, loop quantum gravity arrives, like, Superman saving you, and the squeezing stops, and because you get a maximum squeeze. Quantum mechanics works as sort of repulsion that blocks the squeeze and reopen the space around you, okay? So the space starts reopening around you, and instead of falling down, as you've done at this moment, you realize that you're being pushed out. And you sort of go backward. You're pushed out, and come out of the horizon. Oh, we're saved. We're happy again. And you go out for the horizon, and now it's not a black hole horizon anymore, it's a white hole horizon anymore. It's the same position as before, so you're out. So whatever came in comes out. Only remember the time dilation, which I talked about. When you come out and you look at Earth, on Earth, billions of years have passed. Okay? So, bye-bye your friends and their
just the least of it, yeah.
Children
probably.
and children and children, and who knows? Maybe there are big mosquitoes dominating there. Who knows? Or maybe there's no Earth anymore. It's been taken away by the sun exploding, or who knows. So, if the theory is correct, black holes turns into white hole in the future, and this happened by a sort of bounce. Everything falls in, bounces out, which is take short time if you go through inside, but take very long if you're outside, because from the outside you see all this bounce like a super slow motion. So that's the hypothesis, and that's the hypothesis on which me and many other colleagues are working. And I wrote the book not to tell people, look, this is what's going to happen. To tell people, this is what it is to try in theoretical physics. Try to guess about something. We take what we know about quantum mechanics, we take what we know about general relativity, we try to combine, and this is a possible reasonable story of what happened.
Did You said that Einstein's equations sort of worked up to a point. Did he predict what would happen once you went through the other side, or are you saying that there was a limit and that's basically as far as it goes? It's no longer doesn't work for us beyond that point, or
He very clearly pointed out that his theory has limitations because of quantum mechanics. And he said, in fact, very early, he wrote his theory in 1915, and there is a paper in 1916, so 1 year later, in which he said, and by the way, because of quantum mechanics, my theory will have to be corrected. But he never went into trying to do this.
and this is kind of an open invitation, perhaps, to kind of
Yeah,
advance and
Absolutely.
move our understanding forward.
absolutely. I think people like Einstein had absolutely clear idea that in spite of the immense steps ahead that he did, that was not the end of the story. There was open problems still. Even if everything he did turned out to be true, which actually turned out to be true, there are next open problems. I'm always fascinated by this phrase that Isaac Newton wrote in a letter at the end of his life, in which he says, I quote by heart, I don't know how future will look at me, but the way I look at myself is like a child who is playing on a beach with pebbles and finds some nice pebbles and looking at them in front of the immense ocean of our ignorance. So this is Isaac Newton is probably the greatest scientist ever lived, and the one who gave us, universal gravitation, mechanics, optics. I mean, he just is marvelous, plus mathematics, calculus. And he was absolutely aware that with all he understood, what there was yet not understood was far, far more. And so was Einstein.
And so, as you sit here now talking about the subject matter and the white holes, where do you see as that ocean of ignorance? Where do you see that in the modern world, given our current understandings
Of physics.
Yeah, physics. Where do you
This
see that
is a
space?
crucial question, and it has been a question driving my career as a scientist, and also characterizing, I would say, my career of a scientist, putting me in a slightly outsider position, to go back to your original question about outsiders. Because after the discovery of quantum mechanics, a lot of scientists focused on understanding the atom. Quantum mechanics was understood studying the atom, right? And then the atom is sort of electrons going around nucleus, and the question was about how the nucleus works, and they're discovered as protons and neutrons, and then how neutrons and protons work, because they're also composite things. And it was understood that the protons and neutrons are made by smaller particles, which are the quarks. So it seemed that we were at the end of the story. Just quarks and what you want, the ingredients of proton, neutrons, and electrons were everything, plus light and plus gravity. And then suddenly all sorts of new particles were discovered, the muon and the neutrino, and so on and so forth, which physicists were, oh my God, somebody said, who ordered this? They're not needed, but they exist. And then there was a big work, and what came out of this work in the 50s and 60s, but toward the end of the 60s and the early 70s, there was some clarity in this particle physics, which was put together a theory which today we call the Standard Model. It's not a very pretentious name, but it's a fantastic theory actually, which is particle physics theory. But the Standard Model seemed incomplete. It's not a beautiful theory like general relativity, sort of thing. And the particle physicists try to patch it better. And of course, it did not work well with gravity, with general relativity, because that was not part of it. So there was a move to try to extend this work that was the construction of the quantum of the standard model to include everything. And it was the start of the search for the theory of everything, okay? TOE, theory of everything. And there was one tentative candidate of that was string theory, which seemed to have some aspects were very, very tempting, because it was a relatively simple theory that included all the particles of the standard model, plus gravity, plus light, plus the nuclear forces, plus all sorts of other things. And it seemed to be the possible final theory. So a big part of the community took that as the problem, and that's called the problem of unification. Unify all the various aspects of the world, the physical world that we know, in a single, very simple equation from which everything follows. And the search for the theory of everything has absorbed the mind of, I don't know, I could quote Ginsberg, the best mind of my generations, destroyed by Ginsberg. I think it was the wrong idea. Not the wrong solution, it was the wrong problem. Because I think what I've just said, the best scientists were always aware that we are far from exhausting reality. There is this immense ocean of ignorance that Newton mentioned. There's Einstein who, right, general relativity in 1915 and 1916 says, but, okay, it will have to be corrected because I know there is else. It's just obvious because there's quantum mechanics. And who knows how many things are out there in the universe which we haven't seen yet. Other particles, other stuff, who knows? I mean, just So I have devoted my career, not just me, a part of the community, not to try to find the final theory of everything, okay? It's too ambitious. But to solve specific problems. Like, for instance, what are the quantum properties for gravity? Which means what happens if you go inside a black hole? Just enter the black hole and then what? And that's a concrete problem. Newton was solving concrete problems. How do the planets move? He wasn't writing the theory of everything. And in fact, if he had tried to write the theory of everything, he wouldn't have done what he did.
The way we're talking about space and time over the course of this conversation requires us to conceive of it in a non-linear fashion. And that linear view, the common sense, the orthodoxy, in a way, is the confusion you're talking about. It's the earlier on in the interview. It's the ocean of ignorance, and that actually the scientist's role is to think creatively, to break from the orthodoxy, and to actually illustrate that what everyone takes as received wisdom, what everyone takes as being true, actually is part of a broader confusion that none of us have been able to put our finger on because we've been so immersed in it.
This is exactly the point. This is what you just said is exactly the central point, and it has been also the central point of the scientific work of my life. Let me make it concretely. When you fall into a black hole, you go down there. This passage, this jump from the squeezing to the opening, from the black hole to the white hole, cannot be described in space-time terms, because space itself is quantum there, and time itself is quantum there. So exactly like the particles through the through holes, okay, is neither here nor there, is in both places, but we don't understand well. The same manner, space down there is neither one shape nor another shape. It's two shapes at the same time. So it's not something we can describe in space and in time, which means that to do quantum gravity, to study the quantum property of gravity, which is what I'm studying, we have to accept that our strong natural intuition about a continuous space in which things happen and a continuous time along which things happen, that's partial. That's like the flat Earth. It's good. More or less it's flat. If you build a house, you assume that the Earth is flat. Okay, but it's only good here. It's not good if you want to make a map of the entire Earth. It doesn't work. And so the continuous space and the continuous time are good for our everyday life, but not for understanding what happened deep in the black hole or in the very early universe in these extreme situations. So we have to change something fundamental. So the problem is not to find the final theory of everything on the basis of our conceptual understanding of the world. The problem is to be ready to change our conceptual understanding of the world for learning something new. And that's what fascinated me about science.
I was about to ask you how easy you think it is for someone to change their consciousness in that way.
Well, nothing is easy, but
Yeah.
that's, life is good because it's not easy.
Absolutely. Carlo Rovelli, thank you so much for taking the time. Really
Thank
appreciate it.